Okay, so the geologic time scale. What we need to understand is how relative and absolute dating are different. We also need to understand how Earth's geologic history is classified, as well as some major events in Earth's geologic history. So the geologic timescale is something that we study as geologists, but it's also something that includes the work of paleontologists. So geologists are the ones that study the Earth processes and how sedimentary layers are made, and paleontologists study the history of life on Earth. And so we use our understanding of the layers and the patterns in volcanic eruptions and plate tectonics, and we also use the study of life, and we put these pieces together to understand Earth's history. So the first thing that we need to understand is stratigraphy, which is basically just the understanding of how we use layers to tell age. And the basic law here is the law of superposition, which is just that the oldest layers are going to be on the bottom on the way up to the newest layers. All right, so another thing that we use are fossils, and there are many different kinds of fossils. They're basically the preserved remains or traces of animals, plants, or other organisms, and they can either be made when minerals replace the biological molecules that were there, or when an impression is left in the rock like a mold or a cast. So, fossils. What are the conditions necessary in order for a fossil to be made? Well, first of all, you have to have an organism that's buried very quickly, because if the organism is left on the surface, decomposers or bacteria and fungi will break down the organism. And so the organism has to be buried very, very quickly, and whether it's ash from a volcanic eruption or a landslide or falling into a tar pit, it has to happen very, very quickly. Otherwise, the things will be eaten and decomposed by bacteria and fungi. Layers of sediment usually build up over time over the organism, keeping it intact so it doesn't get disrupted by other geologic events. And it's got to be left for a long period of time. And these structures, the ones that usually are the only ones to remain, are the ones that are bones and teeth or hard structures. There are very few examples in which skin or soft tissue has been preserved in a specific way. Typically, we only have that happen with more recent fossils that were preserved in either ice or in like a peat bog in an acidic environment. Erosion and uplift tends to expose things, so we don't have to dig too far to get to them, but it is possible sometimes to really go digging for fossils. But it's erosion and then isostatic uplift that bring these fossils to the surface. So sedimentary rocks are the kinds that contain fossils. You're not going to find sedimentary rock, or fossils in metamorphic or igneous rock, because the temperatures and the pressures would change the fossils from their original form too much. And we can use the age of the sedimentary layer to determine the age of the fossil, and vice versa. We can use the age of the fossil, if we already know that, to determine the age of the layer. And so it works in both ways. What you should understand at this point from all of these kinds of ideas regarding fossils is that fossils are not something that happen very often. If you think about all of the millions and jillions of organisms that have ever lived on this planet, if you think about how many animals there are alive now, okay, that's a lot of things. Every single bug, every single insect, every single deer, every single squirrel, every single person. There's a lot of living things on Earth at one time. However, how many fossils are there? Not very many. Okay, so the events and the conditions needed to make a fossil are very rare events. And so if you think about, well, how come we don't have, a fossil that looks like this? Well, it's very likely that it just never formed. Or if it did form, it's going to be very difficult to find. Or if it did form, maybe it got destroyed by a geologic event. So fossils are rare. Fossils can tell us a lot about the environment in which an organism lived in and the conditions under which it died. Many times we can find marine fossils at the top of a mountain. So things that lived in the ocean that we find on a mountaintop, that's kind of weird. But it's evidence for continental drift and plate tectonics. Sometimes we can find these marine fossils and we can understand how those layers were made at the time they were deposited as well. Fossils, as you know, also provide us evidence for the theory of continental drift and plate tectonics because we found fossils, identical fossils, on 2 different continents. And they would have had no way of traveling the distances that these continents are today. All right, so geologic timescale and relative age. So this is something that we've already discussed when we were learning about stratigraphy and how to identify the relative age of layers. But relative just is saying about order, not how long something was alive. Like, I am older than my younger sister, but that doesn't tell you how much older I am. We would need absolute age to know that. All right, so if you were to determine which one was the oldest and which one was the youngest, the conglomerate would be the oldest, the mudstone the youngest, and everything in between, yada, yada, yada. All right, so then it can be kind of tricky, right? It's not always as easy as that previous slide because crazy geological events happen, man, and that just messes stuff up. So if you notice here, there's a fault at line E. Line E shows a fault, and we know that the fault is older than D, the igneous intrusion, because it bisects the igneous intrusion and splits it apart. So let's see if you can figure out the order of these layers here. All right, I would say that that blue one on the bottom is the oldest, followed by B, then by A, then D, then E.
Hey, I thought you were doing exercise again. How was it? Fine.
Sorry about that. Fossils, we can use them to determine the age of the fossil record, and they give us a snapshot at what Earth was like in the geologic history. So each layer is like a chapter in the history of Earth. All right, so index fossils. This is where things get interesting and important here. Index fossils are basically fossils that only lived at a specific point in time. They did not live in other time periods. And so basically it's a tool that can tell you what age a rock is. So if you find that fossil, you can go, yep, this is that time period. And if that fossil is not there, then it wasn't that time period. So index fossils are really, really good tools. They're easily recognizable. They were abundant in that time period. They had wide geographic distribution, meaning that not only was that fossil in Africa at that time, but that fossil was in Asia at that time, that fossil was in North America at that time. So it was in all the places, but only at one time. Okay? So trilobites are a really good example. They were a late Precambrian fossil. They were everywhere. There were a lot of them, and then they died. And so they're basically like a time stamp on the Earth saying, if you find this rock in this layer, this is how old that layer is. And everything else that you find in that same layer is the same age. Index fossils are super handy, and they're awesome. So if you take a look at this, which one would have been an example of an index fossil? I see two. One being the trilobite at the bottom, and the other one would be the ammonite. If you got ammonite, you would be correct. All right. So besides relative age, we also have absolute age. An absolute age is like saying exactly how old something is. Okay? And what we do is we use the breakdown of radioactive elements to figure out the absolute age of something. And so we use this property called a half-life, which is an amount of time. and it's the amount of time it takes for the amount of radioactive element to break down to its radioactive product. And it's so basically when it goes from however much there is to half of however much there will be. So for example, where's my pointer? It's not working the way I remember it. Stupid pointer. Okay. So we usually use both relative age and absolute age together to determine how old something is. So, like, let's say you're 12 years old and your grandpa is 72. Those would be absolute ages, and your relative age would be that you are younger than your grandpa. But the words on this side, on the right-hand side, don't explain what absolute dating is. Absolute dating would be if you look at the newly formed rock, all of the uranium in it, there's only uranium in it. But over time, that uranium will turn to lead. And every single time that the uranium goes from however much there is to half of however much there was, that is the length of the half-life. Okay, go ahead and discuss with someone else your understanding of these two things, both relative age and absolute age. All right, so the geologic time scale. So all of Earth's geologic events can be broken up into time periods, kind of like in a school day you have like first hour, second hour, third hour, fourth hour, and all of those different lengths of time are the exact same length of time. However, in Earth's case, this is not how it works. The earlier ones are quite a bit longer, and the more recent ones are much, much shorter periods. So this one gives a better representation of the actual difference in length of time for all of these different time periods. So if you look at how much of Earth's history falls into the Hadean and Archean and Proterozoic, and all of that together is called the Precambrian. Okay, so that's very, very, very early life. Things were a very slow start. Just to develop a single cell, okay, all of that took a very, very short amount of time. And then after that was when things started to explode. So if this were a clock, humans didn't show up until 11:58 p.m. Okay, so basically if life started on Earth at 12 o'clock the previous morning, okay, humans didn't show up until almost midnight the next day. Only a minute and 18 seconds away from the next day beginning was when humans showed up. Okay? Some of the important events happened, okay, over these 4.6 billion years. All right, so the Precambrian is that portion that is 88% of Earth's history, and it's broken into three parts. Okay, it began approximately 4.6 billion years ago, and the oldest rock fragment that contains a zircon mineral was discovered in Australia, okay, 4.4 million years ago. And this is basically very primitive forms of life. Single-celled organisms, bacteria, and jellyfish only existed then. Then we move on to the Paleozoic era, early life. We had the supercontinent Pangaea, we had marine life, and invertebrates, we had fish, ferns, and amphibians. And then a mass extinction brought the end of the Paleozoic era. Following that, we had the Mesozoic era, or life on Earth's middle portion, in which you have dinosaurs, small mammals, birds, conifers, flowering plants, and the petrified forests in Arizona are an example of a fossil deposit made at this time. But another mass extinction ended the Mesozoic. All right, then we get on to the late life or Cenozoic era, and we are just the last little bit of this era is when we come along, and we are currently in this era. Large mammals existed in the Ice Age. Human beings came late in that time period, and periods of ice ages played a role in the formation of geologic features we see on Earth today. So what we are looking at, like Minnesota, we are living in the remnants of the Ice Age right now with the glacier till that we're growing our plants in right now. And some of you may not realize this, but the time that the pyramids were built, there were still mammoths living in the Arctic. Yeah, pretty crazy. So we are just getting out of the Ice Age, basically. All right, so imagine you had a sheet of paper and you were to divide it up, a football field, into all of the different eras of life on Earth, and you were to mark your field. What would that look like? Well, 0 to 87 yards would be Precambrian. 87 to 95 yards would be Paleozoic, or early life. Mesozoic would be 95 to 98.5 yards, and the Cenozoic era would be the last 1.5 yards. All right, so we take these eras and we break them down into smaller pieces called epochs. And so we live in the Holocene epoch at the very top. Okay, and so whenever you hear like Jurassic Park, that was the middle epoch of the middle era. So if you look on there, there's the Mesozoic era, and then to the right you see Jurassic. And so that tooth fossil that I found in northern Minnesota was part of the Cretaceous epoch. Okay, and that is just a little bit later than the Jurassic era. There were quite a few different extinctions that brought the end to a lot of organisms on Earth and really shaped things and life on Earth. There was the end of the Ordovician, the late Devonian, the end of the Permian, and the end of the Triassic, and the end of the Cretaceous. And these are at different points in Earth's history that we saw that a lot of organisms died all at one time. And so oftentimes we think that there was only one extinction, like, oh, the dinosaurs were taken out by a meteor. Well, that was one of the mass extinctions. But in fact, there were actually 5 mass extinctions, and the biggest one was the end of the Permian era, 245 million years ago. So the most recent one happened 65.5 million years ago at the end of the Cretaceous. And it brought about a lot of climate and geologic changes that made it difficult for the dinosaurs to survive, and initiating the Ice Age. This one was most likely a meteor strike. All right, so what you need to understand the difference between relative age and absolute age, how one is just older or younger based on what layer you're in, and absolute age is using radioactive dating and half-life. You need to understand how half-life works. You need to understand what index fossils are and why they're helpful. You need to be able to look at a geologic time scale and be able to say, okay, so this was a really large period of time, this was a short period of time, and where we come along is a very recent in Earth's history, and Earth has a large history before us as living things. The other thing you want to do is be able to describe a few major events in Earth's geologic history. All right, the end.